The point of exercise 2233 is to show you that you can do SN2 reactions with alpha carbons as nucleophiles. So up until this point in this chapter, we've shown that if you add a base to any of these ketones or aldehydes, or for that matter, if you add an acid also, you create a nucleophilic position on the alpha carbon. And once you have a nucleophile, all of the possibilities of nucleophiles in general are open to you. So you can do substitution reactions, where a nucleophile comes in and a leaving group leaves. Now there are two bases that we're going to see in this exercise, and they each fulfill a slightly different function. If you look at our original ketone here, we know that the alpha carbon will be able to be turned into a nucleophile if it has a hydrogen on it that can be stolen. Now both of the alpha hydrogens here, both of the carbons that are one atom away from the carbonyl, both of those alpha carbons have hydrogens on them, but they are not equally substituted. This carbon on the left is bonded to 1, 2, 3 other carbons, so it is tertiary. And this carbon on the right is just bonded to one other carbon, so it is primary. Remember that those designations give you information about how crowded a carbon is. So this tertiary carbon is much more crowded than this primary carbon is. We can control which of those hydrogens are stolen by the base by using either a very big base, like a very bulky base. The bulky base will be able to reach this less crowded hydrogen better than the more crowded one, or by using a very small skinny base. And so the two bases we're going to use are LDA, that's our bulky base, and hydride. And really, it's usually paired with sodium, so sodium hydride. Let's talk about each of these one at a time, and then we'll apply them in these exercises. So we've seen LDA before. LDA stands for lithium diisopropyl amide. So actually, I'll fill these in as we draw them. If you remember, NH3, ammonia, the nitrogen version of water, is a weak Bronsted-Lowry base. This is sort of the poster child for a Bronsted-Lowry base, because it has that lone pair on the nitrogen that it can accept H pluses. Now, if you take the conjugate base of that base, so you remove an H and a plus sign, so you start with 0, if you remove a plus charge, then you have -1, then you end up with a really strong base. And you used this strong base, amide, in Organic Chemistry 1 to rip off the hydrogens of terminal alkynes to make those carbon nucleophiles. Here, this amide is going to be the A, in LDA. Now, this is a strong base, very strong base, but it can also act as a nucleophile because it's relatively skinny, it can reach its way into things. And so we can turn it into just a base, and we can turn it into a bulky base. If we replace the two hydrogens, so those hydrogens were here, if we replace those hydrogens with sort of bulky carbon chains, and in this case we can use two isopropyl groups. So that's diisopropyl. So you have two isopropyl groups coming off of the amide. Now the amide is still just as basic, it's still just as strong of a base, because the nitrogen has two lone pairs and a full negative charge. It just won't be able to get into narrow or crowded areas because it has these big bulky tails on it. Now the negative charge is very reactive, and so to stabilize that while the molecule is being stored, you add a lithium cation. And so the lithium cation with its positive charge balances the negative charge on the diisopropylamide. And so that molecule there is lithium diisopropylamide, or LDA. LDA is a very crowded molecule, and so it will prefer less crowded hydrogens. It'll be hard for LDA to reach into this tertiary area. It tries to get there, and its big fat tails bump into the way, but it's easier for it to get to this hydrogen on the primary carbon. And so that's the one that it preferentially steals. Now another thing is that will help it to steal this less crowded area is this temperature. Now, there's a long thermodynamic explanation for that, but in general, you could imagine sort of intuitively how if this is at a lower temperature, this is not bouncing around as much, these bonds are not twisting and turning as much, and so this hydrogen is not exposed as much. And this isn't pushed to dive into the belly of this molecule quite as much at this lower temperature. So that's LDA. LDA will prefer the less crowded hydrogen. Here, the primary hydrogen, it will steal that. The electrons will snap back onto that primary carbon there. And what you'll end up with after that first step is a carbon nucleophile on the alpha carbon of the less substituted, alpha carbon. So this right here. Okay, so we used LDA to preferentially create the nucleophile on the less substituted carbon. Now in the second step, we're adding methyl iodide, or iodomethane, whichever you prefer. And what should stand out on iodomethane is the halogen. Halogens, chlorine, bromine, iodine are awesome leaving groups. So this nucleophile can swoop in, attack the carbon, and kick the leaving group off at the same time. We have nucleophilic attack, loss of a leaving group happening at the same time. That's the signature of an SN2 reaction. And so what you end up with, and I'll draw this first in a way that looks more similar, but then in a more standard way. So let's move this one hydrogen over. And these electrons here are going to make a new bond from that alpha carbon to this carbon here. And the iodine will be floating around, living its best life somewhere in the solution. And so if you wanted to just draw this just as a pure skeletal structure, you would erase this carbon, all the hydrogens will be implied, and there you go. There you have it. So this is your product. The takeaway from this is that you can do an SN2 reaction with these alpha carbons. Alpha carbons are nucleophiles, and you can use nucleophiles to do SN2 reactions. And the big thing is you can prefer to form the nucleophile on the less substituted carbon, the less crowded carbon, by using LDA and making the temperature a little bit lower. The other base that I wanted to talk about and that I mentioned earlier was sodium hydride. Now, anytime you see a metal, you know that the metal has very low electronegativity. So it gives its electrons away, and here it'll give it away to the hydrogen. So you have a hydrogen with 2 electrons. A hydrogen with 2 electrons is called a hydride ion. So this is called sodium hydride. And you would have seen this before when you talked about carbocation rearrangements in Organic Chemistry 1. You saw hydride shifts. Hydrides would shift over. That's hydrogen atoms with 2 electrons would shift over to the less stable carbocation to create a new, more stable carbocation. So you would have seen that before. And if you look at this, you'll notice that it is a very strong base. Hydrogen is the smallest atom on the periodic table. So if you try to stuff a full negative charge in there, it's going to be, the charge is really going to repel, the electrons are really going to repel each other in that tiny space, and it'll be very unstable. So this is a very strong base, and it's also kind of beautiful because when it steals a hydrogen, when it acts as a base and steals a hydrogen, it turns into H2 gas. And you might remember, if you can ever form a gas in a synthesis procedure, do it. It will increase your yields so much. If one of your products is a gas, the gas naturally bubbles out of solution. And so you're constantly removing products, and through Le Chatelier's principle, that shifts the equilibrium to the right. So in this first step, we're going to treat this with this hydride base. And as the equilibrium gets shifted to the right, you improve your yields. Now, again, we have a ketone, and you have 2 alpha carbons, 1 on each side. But you'll notice this one on the left is bonded to 1, 2, 3 carbons, so it's tertiary. The one on the right is just bonded to 1, 2 carbons, so it's secondary. So, in this case, this small base will be able to reach the hydrogens on either of these pretty equally well. So you'd have a hydrogen on each one. So the crowding is not an issue here. The only issue is which position produces an ion that's more stable. So for example, you can imagine this hydrogen stealing this here and the electrons going back on that alpha carbon, in which case you would make this ion, or you could imagine, theoretically, this base stealing this hydrogen and the electron snapping onto the other alpha carbon and making this ion. So if you're trying to think about, since this skinny base, this tiny, tiny little base that can wiggle its way through any little crevice, since that base can reach either of these hydrogens equally well, the only question is which one is more stable. And it turns out that the more substituted one is more stable. Both of these are allylic to the pi bond, and so in both of them the ion will be stabilized through resonance. But in the tertiary one, in addition to that, the charge can be spread out and stabilized through hyperconjugation. This lone pair exists in a p orbital, and this sp3 hybridized carbon has an sp3 orbital that almost kind of lines up with the p orbital and allows it to bleed out into it. The more carbons you have, the more sp3 orbitals can do that, and so the more spread out and stable the lone pair becomes. So in this case, the more substituted lone pair is more stable because of that hyperconjugation. That allows the charge to spread out more, and so of the two options, the hydrogen ends up stealing the more substituted hydrogen, or the hydrogen on the more substituted carbon, to produce the more stable product. So this is the opposite of LDA. LDA steals the hydrogen on the less substituted carbon. Sodium hydride steals the hydrogen on the more substituted carbon. So you can preferentially make either of those carbons a nucleophile. So that's the first step. Once you have that molecule, that carbon nucleophile, you could treat it with any leaving group, any alkyl halide, and do an SN2 reaction. So here it looks like we have the bromine on the benzylic position. So we have benzene, really toluene, with a bromo on it, so bromotoluene. That's what we have in the second step here. And so this nucleophile can just do a normal SN2 reaction. This can attack that benzylic carbon and kick the bromine off. So that you end up forming a new carbon-carbon bond, but it's really through an SN2 reaction. Nucleophilic attack and loss of a leaving group. So onto this you'll have the methyl group and then the benzene ring. And so that would be your product there. Okay, so we learned we learned a couple things. First, you learned that you can do SN2 reactions using alpha carbons of enolates as the nucleophile. So you just create the enolate and then treat it with an alkyl halide. Preferably a primary or secondary one. A tertiary alkyl halide, as you remember from Organic Chemistry 1, is too crowded to allow for an SN2 reaction to happen. And the second thing we learned are using different bases to create the enolate on different alpha carbons. If you use LDA, lithium diisopropylamide, that will create the enolate on the less substituted alpha carbon. And if you use sodium hydride, that will create the enolate on the more substituted alpha carbon.